So now let's try to prove the second step in our proof. Basically, I want to show that the image under this phi from G to G double hat is a closed subgroup. So from last time, we saw that this map is a homeomorphism from G to the phi of G to its image in the relative topology. So automatically, you have that the image is a locally compact subgroup of the G double hat, which is also locally compact as well. And in reality, we have this following lemma. So in fact, as long as you have a locally compact subgroup in the relative topology of a locally compact Hausdorff group, then your subgroup is automatically closed. Okay, so essentially we just need to prove the following technical lemma. So let's try to prove this. So first of all, if you have, let's say G is locally compact Hausdorff and you have a locally compact subgroup in the relative topology, by the locally compactness, you can find that there exists a U inside that's open inside the G. So because I have a relative topology, so I might as well just say, well, open in where? So let's say U is the open neighborhood of the identity. Then you have this U intersect H, that's going to be an open set inside your the G. And by the locally compactness, I can take the closure, this is closure inside U, inside H, so let's call it K. So that's going to be compact, okay? That's going to be compact inside H. So, but if you have something that's compact inside H, I want to first of all show it's actually also compact inside G, because, well, if you're K, well, think about it as a subset in G. So if it's contained in some union of some open cover, then it's also contained in, because K is a subset of H, so K is also inside the U alpha intersect H. So because K is compact in the relative topology, so you can find some subcover, so it's contained in the union of this U alpha I going from 1 to n, okay? So that's basically shows that inside H, which is inside these covered by U alpha I, okay? So every open cover has a finite subcover, so I have that's also compact in G, okay? So K is also compact inside G, and because it's also compact inside G, it is quite clear that this K has to be the closure of this U intersect H in G as well, okay? So in other words, K is just going to be equals to U intersect H. This time you take the G closure, okay? So because this K is going to be compact and is containing this set, okay? All right, so now we prove this basic fact from the topology. So in other words, if you take the closure of something in the relative topology, if the closure is compact, then the closure inside H and K are basically the same. So now let's suppose that I have some, say, V, so that open neighborhood inside G, so that V is equal to V inverse. And I also have V times V is contained inside this U, so U is something with a compact closure. All right, so I should also say identity is inside V. So now I want to show that the H closure is just H. So let's just pick anything X inside the H closure. I want to kind of break it as a product of two things inside H, okay? So how do I do that? Well, first of all, let's just pick a net X alpha converge to this X, so that each of these X alpha is inside H. All right, because this X alpha is converging to X, so I can find some tail, so that there exists some, say, alpha 0. So that for all the alpha greater than alpha 0, this X alpha is close enough to this X. So I can have these X alpha is going to be inside the X times V, okay? So around this neighborhood. All right, so now let's consider the following. So if I consider the V times X inverse, okay? Because X is inside H closure is clearly the group. Because H is also a group, so the X inverse is going to be inside the H closure as well. And so because X is inside H closure, X inverse is in H closure, So this neighborhood of x inverse has to intersect this h somewhere, okay? So if I consider that intersect h, there exists y, okay? So there exists a y, so that is in this intersection. So now let's break this x into these two parts. So first of all, I can write x as x inverse times y inverse times y times x. So why do I do that? Well, the first part, this y inverse, we know that's inside h because y is inside h. And what about the second part? Well, the second part, I have y times x, which is the limit of the y times x alpha because x alpha is converging to this y. And so each of these y, so if I look at this y is inside v times x inverse. But this x alpha, where they're from, well, when alpha is large enough, they are going to be inside x times v, so around this neighborhood x times v. So, and if you multiply these two things, the x get cancelled, so this is v times v, so that's going to be contained in this u, okay? Not only is going to be inside u, it's also going to be inside u intersect h. Well, now we prove that I have yx is the limit of this u intersect h. So that's going to be inside the u intersect h closure. Well, this closure, you can think about this closure inside G, but we just proved that this closure is also the closure inside H. Well, also this closure has to be inside H as well, okay? So in other words, this y times x is also inside H. So this just shows that x is a product of two things in H, so x is inside H.